Hello and welcome to this section of the course. My name is Gerd Berner and I'll be presenting overview of maritime operational technology. Most of us are familiar with the term IT or information technology. Operational technology focuses on monitoring and control of machinery and is often found on board ships in the engine room. We'll touch on this concept further in the following slides. So as we consider OT systems on board ship, we will look at what makes them work, how they are designed for redundancy, which is a critical requirement for OT systems. When I say redundant, I'm talking about duplication of certain key functions. For example, a power supply or a storage device. If one power supply fails, the other power supply allows a continuous supply of power so that the OT system continues to deliver its critical function. What are the considerations for seafaring staff and shore-based engineers to maintain systems so that they are reliable? These are all key questions. And how can we monitor to detect problems, either proactively or reactively? We'll discuss how data is collected from field devices and how that data, and when I say field devices, I might be talking about temperature sensors, pressure sensors, various switches within the engineered environment of the vessel that all come together to provide that end-to-end system that keeps the vessel safe and operational. So, as with any technology system, there are common building blocks, and many of those will be familiar to us. Compute engine, there'll be software, there'll be memory, so short-term memory and long-term storage in the form of potentially magnetic or solid state disk drives. A power supply, as I've mentioned, oftentimes that might be a redundant power supply with multiple independent modules, and that's fed from the ship's generating plant. And as I've said, all of these systems will have some level of built-in redundancy in the event of failure. And that level of redundancy should equate to the criticality of that particular system. So, just to be clear, we're not learning how to operate these technology systems. We're looking at them from an engineering perspective and understanding how they're put together. So we'll be talking about systems including bridge systems, engine room systems, stability, cargo, and we'll touch on business systems because obviously a vessel at sea is a part of a larger business, and you will see systems on board that are supporting that connectivity ashore. Systems are integrated and share a common network on board. How technology systems are deployed to operate and manage the vessel. Good practices need to be applied to keep them operating effectively. And this course will hopefully assist seafarers to develop skills to cast a critical eye over the design and operation of technology on board ships. In many cases, that technology support can be outsourced. However, where you have this type of outsource arrangement, it's often performed remotely. And at the end of the day, it's the seafarers who are impacted if technology systems go wrong. So it's very valuable to be able to be an active contributor in that conversation with shore-based support people. Yeah, and we want to empower seafarers to be in that conversation, particularly when systems like OT systems have a human-centered design impact and can impact safety outcomes. So we'll take a principles-based approach and apply that to all technology systems, regardless of their purpose. So I guess the overall outcome is we're trying to get the highest level of reliability, redundancy, and the ability, if necessary, to understand these systems so that they can fall back into a degraded mode if necessary, and we've still got the skills to support operational technology on board. So as I've already said, this course considers operational technology, OT, but also considers how it interacts with IT on board the ship, because the two are typically connected. So IT systems found on board, we've got networking devices, hubs, switches and routers, and many of us are familiar with these types of devices because we have them at home. Typically, the devices we find on board ship are more robust and built for more challenging environments. They might be rated in some cases to operate in a far more extreme environment, environmental conditions. And in another section that I'm covering, we will talk about the impacts of environment on technology. We will also find workstations, typically in the ship's office or distributed around the vessel, often in the engine control room on the bridge, various workstations performing different functions. There's usually a clear delineation though between the IT workstations and the OT workstations. Once again, OT, a workstation found on the bridge that's part of the systems that actually control the vessel, is treated very differently to workstations found in the office that are running Microsoft Office, spreadsheets, documents and the like. The level of robustness is obviously quite different due to the criticality of the mission of that particular workstation. When I say workstation, I'm talking about a computer installed with Microsoft Windows or something like that. Servers are typically found on board vessels, generally out of sight, hopefully in a comms cabinet or a secure area, a server room if there is one available. And those devices are typically not logged onto by users, but they're performing a function like a mail server, file server, or domain controller, which is a device which manages a Microsoft network. Those devices require maintenance and professional support to keep them running well, and that's a key requirement around our onboard systems. Firewalls, many of us are familiar with firewalls. They segregate networks and protect computers from connections outside our trusted networks. SATCOM terminals, these are the devices that provide connectivity to vessels while they're at sea via satellite. So in effect, equivalent to our shore-based broadband routers that connect us to our internet service providers. So we will be covering techniques to identify faulted hardware and software within the course. And we're hoping to develop skills, as I've said, to participate in technical conversations. This can be very useful if equipment is not functioning while you're at sea. And if you have engineers on board repairing or modifying the installation, we do often hear of stories of installations when engineers come on to install new systems. They're often operating under very tight timeframes, and shortcuts have known to be taken to get the equipment installed so the vessel can leave. And as I guess the ultimate end users of that equipment, it's very useful if seafarers can converse with those engineers and ask questions and raise concerns around the installation of a new piece of equipment. Always useful if you can represent the company's interests if you believe that something's not meeting the necessary standards when new equipment is either installed or existing equipment is being serviced or repaired. This course will cover both the concepts of automation and autonomy. There's a key difference. Automation is largely supervised by humans, and autonomy is a class of systems that can operate without any human supervision or interaction. So throughout history, technology has obviously evolved, as it has in all fields. If you take a closer look at the field of maritime, post-sailing ships, we had many roles on board ships that are no longer present. So stokers and trimmers who would feed the boilers with coal. We had radio officers who were in charge of communications, and quartermasters who steered the vessel. And all of these roles have been essentially made redundant through the use of technology. The transition to oil-fired boilers and engines, radio officers, that role has, through technology, even though the underlying principles of radio transmission haven't really changed, the user interfaces and the technology, the computing systems that front end those radios are now have evolved to the point where that role can just be performed by the deck officers. A lot of the skills that were needed to make those radio calls have been taken over by computers. Quartermasters obviously were replaced by autopilot systems, and for those who have spent time at sea, will know that very little actual steering of ships occurs apart from when entering port. So we can see automation at work on the bridge. Autopilots, as I mentioned. We've got computers managing stability, managing cargo handling. In the engine room, we've got, historically, we would have had ratings, doing rounds in the engine room, reading gauges, filling in logbooks with periodic measurements every 15 minutes or whatever the standard was. These gauges were all machine side, and now we have the luxury of centralization. So a single computer system, for those who have been on board ships in the engine control room, everything, all the readings of pressures and temperatures, positions and what have you, are now gathered by computers and are able to be displayed in many different flexible ways from that central engine control room, reducing the need to continually do rounds, and also providing that informational advantage of that single pane of glass which can provide insight into any aspect of the machinery and how it's operating. The development of automated controllers also played a big part. In the past, critical parameters of the operation, the fuel feed, into the boilers. The amount of water flow was manually controlled, either by engineers or by ratings who would have the task of standing by a particular piece of equipment and manually controlling its key parameters. That is all now automated with controllers capable of controlling boilers, and lots of ancillary machinery has a specialist controller attached to it, taking over that task. Some might say, reducing employment, reducing opportunities for people to perform these roles. Others might argue that these roles are not fulfilling. They're menial roles that are better controlled by computers. Computers can certainly perform them in a very repeatable fashion, and however, there are arguments, as I've said, for and against, and there is always the ethical questions to be answered. But also, when machines go wrong, they do tend to go wrong in a big way. So in terms of catering for failure scenarios can be very challenging, particularly when you have microprocessors involved. And almost all of these systems will be microprocessor controlled. So bridge systems have evolved in many ways over the last few decades. We've transitioned from purely analog systems to systems where we have a digital front end. Now, in many cases, this has been done to assist the users in understanding and operating those systems. And marine radio is a good example of that. The underlying transmission and reception of radio signals is still very much the same as it has been for decades. The front end that presents information to the user and allows the user to operate the system has now been given a digital interface. And generally that is in the name of usability. In some cases, however, user interfaces that are not well designed can cause problems, and Margaretta will be no doubt discussing that during the course of this course. Historically, bridge systems were also standalone and were typically discrete boxes that were installed on the bridge. Many of us who've visited vessels will now know that there's the concept of the integrated bridge. And the integrated bridge is a series of modules that are typically networked together and installed in a console that essentially presents these systems as a cohesive collection of tools that the navigators use to navigate and operate the vessel. The development of ARPA radar, ARPA standing for Automatic Radar Plotting Aid, is another significant development in maritime technology. This ARPA tool basically took what was traditionally a solely analog tool, and radar screens of the past were literally providing a visual representation of the energy bounced off targets and presented straight back onto a screen. The ARPA system allowed for a computer to interpret that information and to present it onto essentially a cathode ray tube or a more traditional computer monitor, and also overlay additional information that assists the navigator in interpreting the signal. So it might be plotting the relative motion, a vector against the target which shows course and speed, or some additional vessel identification data, that type of thing can be added once you have a computer as part in the loop. So that was the development of the automatic radar plotting aid, which happened quite early in the evolution of computers in terms of maritime technology. Some other evolution that's occurred, radio direction finding is technology that's been around since World War II, becoming a little bit passé these days. Deca and Loran are other radio-based navigation systems which have essentially become redundant now that GPS is the primary method of fixing position. One of the other key technological changes, development of ECDIS electronic charts, replacing paper charts. So the ability to download chart information and overlay that now on a common display with radar signals and additional key pieces of information around manoeuvring the vessel. So very much a aggregated display that was never possible in years gone by. So in these, many vessels now will have a common command centre that includes technology for navigating the vessel, for cargo operations, emergency response, all of these activities operating out of this same command centre. So the integration of various pieces of bridge equipment provide a real informational advantage. It allows us to have a single navigational display that synthesizes ECDIS chart data, ARPA radar target data, additional information such as gyro compass, speed log, all to be synthesized onto the same display. This gives the advantage of navigators being able to look at a single pane of glass, single piece of technology to derive all the current information relevant to the navigation of the vessel without having to consult with different pieces of technology. Obviously, this single pane of glass then plays a very critical role, and the usability of that screen and that user interface has to be very carefully designed to prevent any misunderstanding at critical moments. Some other notable points in the development of maritime technology include the development of voyage recorders, which record key parameters of the vessel's operation and also record conversations on the bridge, much in the way that an aircraft black box does. We also have a transition from purpose-built electronics, which was very much the rage in up until the early 2000s. A manufacturer would build from the ground up a radar system or an autopilot, whereas these days the economics dictates that technology systems are built on what's known as COTS infrastructure, common off-the-shelf systems. That's the acronym COTS. And the functionality of the particular system is built in software rather than being built in hardware. So under the covers of a radar system or a charting system, you will find Windows Server typically or Linux running as the engine of that system. So is this upside or downside? What are the downsides of all this technology automation? We have additional capital cost. It's much cheaper to build a system that is operated manually by humans. Capital cost is then offset by operating cost of having more people who require certain skills to deliver that safe outcome. And economics being what it is, it would seem that certainly in the Western world, it is more advantageous to companies to automate and remove that ongoing cost of human labour. Additional complexity is something that needs to be considered. By placing all these very technology heavy systems on board vessels, you need skills to maintain and repair that system. You need the people who can perform those roles, and you also need to be able to have them where you need them to perform those roles when required. Very challenging in maritime industry, of course, when you've got vessels travelling the globe and also the potential for breakdowns to occur at sea. You then have to have a way of providing that, recovering that system with the skills you have on board or via remote assistance, these types of things. And finally, de-skilling of the operators. So in days of old when we had people manually steering the vessel, or we had people manually operating the boiler, when there's a problem and we need to revert to manual operation, those skills just don't exist on board, or to an extent. So all considerations of that have to be taken into account when we go down the path of automation. Communication systems. So on board, communications are covered by regulations known as GMDSS, Global Maritime Distress and Safety Systems. And to broadly discuss these, we have VHF radio for line of sight comms, HF for long range voice. We now have satellite communications that give us global voice and data connectivity. And data connectivity to ships, we'll look at in more detail in the sections on cybersecurity. Communications such as VHF and HF have evolved. Back-end radio, as I've said, is largely unchanged. New digital front ends. And the upshot is we have very much more in terms of microprocessors in service on the modern bridge. So to pose a question to the class, and obviously this is pre-recorded, so I can't hear the answer, but why have we not seen a transition to digital radio like we have ashore? That's the question. And the answer is backwards compatibility. So in the maritime industry, changes in technology are typically very slow because we are catering for the lowest common denominator, and we obviously need to maintain communications across all types of vessels from every corner of the world, and backwards compatibility with to make a change around maritime radio would have huge ramifications. So very, very difficult to coordinate and legislate for such a thing. So along with all those various types of communications we see on board, obviously now, email, we have digital selective calling on VHF radio, and as I've said, we've evolved from purely analog devices to analog devices that are digitally controlled. One very important factor is where we have microprocessor control is we need to be able to maintain the life cycle of that software and apply patches, keep it up to date to reduce the opportunity for cyber vulnerabilities, which we'll be touching on in the course. Now, most people in the room, I'm sure, have an appreciation of the critical nature of maintaining vessel stability and structural integrity. And computer systems are playing an increasing role in ensuring these requirements are met. So container vessels, for many decades in fact, have been using advanced technology to not only maintain stability and integrity, but also efficiency in terms of minimising the backloading of containers. So planning the loading of the vessel with a view to minimising the number of containers that need to come off in a particular port to allow the discharge of containers that are destined for that port. Now, in computer science, that's quite a challenging application. Not only do you have to, at a micro level, look at an individual vessel, but you need to consider that one vessel is part of a broader ecosystem of other ships also loading and discharging. Modern tankers can carry very sophisticated technology systems also that are capable of managing loading and discharge operations of multiple grades of cargo, while simultaneously covering ballasting operations to keep the vessel within a certain bending moment. These, just a few decades ago, the amount of computing power that was available on board would not have supported these types of sophisticated operations. And, a few short decades ago, we were still reliant on manual soundings of tanks and handwritten loading plans. The level of sophistication that can be found on a modern tanker has jumped by an order of magnitude. So as we've transitioned from largely manual operation of vessels to more of an automated footing, the resilience of the systems has become more and more critical, and the integrity of the data that feeds those systems. So when I speak about data in a operational technology sense, I'm referring to readings from networked sensors that may be temperature, pressure. And there are a number of examples from aviation where bad sensor data has led to disasters. Some of the best known ones are Air France 447, Aero Peru 603, and in shore-based industries, the 3 Mile Island nuclear accident. In each of these notable cases, a failed sensor provided erroneous data to the operational control system, leading the system as a whole to exit its normal safe operating bounds. The human operators were then forced to step in and take manual control of the system. And this leads us to this section on the slide around human factors implications. To take manual control of that system, it's necessary to first have the ability and the willingness to step in an emergency under stressful conditions. And humans operating in an oversight role, particularly when they have to suddenly respond to unforeseen circumstances, tend to perform not at their optimum. The humans, to take control in that situation, need to understand the capabilities and limitations of the system and the business rules that the system is trying to achieve. So in the case of a boiler control system, the key parameters of the pressures and temperatures and coolant water flows, these types of things. The training is required for them to perform that role. So in some cases, companies have the view that automation removes the need for training. However, It in fact just changes. There's still that high level of understanding required, but the human is actually performing a slightly different role of monitoring the system rather than actually taking the minute by minute operational decisions. The awareness of modes within automated control systems becomes very important. Mode awareness and the underlying rules that the system is following in varying modes is key to the operator maintaining awareness of how a system will respond in a certain set of circumstances. And mode awareness we find where there's been an error or an incident regarding an automated system, a lack of understanding of all the implications of certain automated modes is often a contributing factor. Okay, so the next class of systems are what we call crew welfare. These systems provide things like internet connectivity, and internet connectivity is very much assumed in modern society. Many crew agents report that internet connectivity is a key determinant in whether crew will accept a contract on a particular vessel. And while this connectivity is desirable and we all seek to stay connected in the modern world, it also presents a number of risks to the other onboard systems. So coming into on board a vessel, we'll have various crew members all with their own, what we refer to as BYOD devices, or bring your own devices, laptops, tablets, phones. These may or may not be maintained to a high level in terms of patches and security fixes. There's an opportunity there for sharing of files on board in an uncontrolled manner. And really the crew welfare network is potentially a very high risk place in terms of cyber threats. So as we've spoken to in previous slides, we have some very critical systems, operational systems performing key safety roles on board, navigating the vessel, providing crew or officers on the bridge with their situational awareness. We've got systems in the engine room performing control functions over very critical pieces of equipment, propulsion and ancillary systems. So we have to very carefully segregate these systems. We cannot afford to have a virus or a worm that is live on some piece of what we would refer to as unmanaged equipment, a BYOD device, then infecting a system, a critical vessel system. So there is potential for a malware infection, and in a lot of cases, the fallback position to a failure of one of these key operational systems would be to fall back to manual methods. And by that I mean, if your autopilot fails, you return the ratings to a watch system to do manual steering. Or similarly, if a boiler controller fails in the engine room, you would have a rating or an engineer who's manually controlling that boiler to continue to provide steam to the vessel. The problem is, as the industry's evolved, the skills to perform that manual role and the number of crew we have on board just will not support this fallback to manual methods. So it does present a significant risk to the safety of the ship. Web content filtering is a capability that we put in place in many cases to protect an endpoint, a BYOD device or a corporate workstation from an infection, from accessing a malicious website. So these systems would typically maintain a list of what we'd call a blacklist of suspect sites, and as the device tries to connect through the browser to a suspect site, that access is rejected by way of protect that device from a malicious infection. The other big issue that we do see is the sharing of files via USB and the use of USB as a charging opportunity, where we have a USB port on a particular, say an integrated bridge system might have a USB charge port to allow for software update, and the watchkeepers see that as an opportunity to charge their phone. What they're not realizing though is that USB, when their phone is plugged in, the phone's mounted as a USB device to the underlying computer system that might be providing the integrated bridge, the ECDIS, the AIS, the autopilot, whatever it might be, and any malicious files that might be on that device that was innocently put there to charge might then infect a critical system underneath. And there's been a number of real-world incidents where this has occurred. Interestingly, one anecdote that I'm aware of is an infection that occurred on a vessel's bridge around a USB device and a phone plugged in to charge, resulting in the infection. And the company posted a notice to say, please do not plug your phones into the bridge equipment to charge them. And following that, the rate of malware infection actually went up on bridge equipment. And the thinking is that people in receiving this notice, then rather than saying, well, okay, no, I'm not going to plug my phone in, it actually brought a number of people's attention to the fact that there were charging ports on the bridge, or USB ports. And as a result, more people were actually plugging their phones in on the bridge. So it's food for thought. Machinery and propulsion management can be further broken down into main propulsion. Now, many of us are familiar with the different propulsion options. We might have a fixed direct coupled propeller. We could have a variable pitch propeller. We could have a gearbox in place with a reversing operation. Now, in each case, the software that controls the main propulsion system will play a role in encapsulating the rules and the way the system operates. So in the case where there is an actuator, say, for a variable pitch propeller, the control system for the main engine will have awareness of the propeller pitch at any given setting, and it will allow the engine to provide the necessary, provide feedback to the governors to provide fuel flow so that engine performance can be maintained at various propeller pitch settings. So just as an example, there will be various integrations from a safety perspective. So the engine control system will have an awareness that some auxiliary systems. For example, the lube oil system is running to provide lubrication for the engine. The engine will not be able to run without that dependency satisfied. One of the roles of that control system will be optimizing combustion, making sure that we get optimum fuel burn. So the fuel system will provide fuel to the engines to consume, and the fuel will have to meet a certain specification. And we'll have an OT system that will be monitoring it'll have the ability to measure the viscosity, the temperature of that fuel as it's delivered, and provide a control input as that fuel varies. The controller will have the ability to increase the heating or whatever might be required, or decrease the heating to maintain that fuel within specification. Cooling systems, taking jacket water from the main and auxiliary engines, will have the ability to monitor that outflow temperature and divert that cooling water to a heat exchanger, or return it to the loop, depending on what the set point is, and doing a comparison with the measured temperature. A lot of these systems are interdependent and have awareness, are integrated with each other, and have the ability to vary set points to keep the whole system running within specification. Power generation is quite a complex system of managing electrical load, of awareness of the generating elements and the consumers, and matching electrical load to provide as an efficient solution and minimise fuel burn at any given time. Also advanced functionality like preferential trip in the event of a loss of a generator, prevents a shortfall on the switchboard. These power generating systems, or power generation management, can trip certain loads to make sure that the whole system doesn't black the ship out. We've got steam systems, once again another combustion system similar to what we've discussed already, and steering systems, maintaining rudder position, integrating with our bridge systems, our autopilots and helms, to optimize the movement of the rudder to keep the vessel on track, and once again optimize efficiency. Cargo systems, depending on the vessel type, integration to manage stability, to manage bending moments as part of the loading operation. To do this, these systems have to be tailored to the vessel that they're installed on. It has to have awareness of the capacities of the pumps and the tanks, and how much ballast can be moved by the pumps in a given hour, and provide that overall equilibrium so that the vessel stays within its operating specification. And business systems, and we have spoken briefly about business systems already. We have significant paperwork involved in running a ship, and often seen as a distraction by the officers on board. And we have touched on this already. We have workstations, we have servers, we have email, often on board an email server. We have the ability and the need to share files, and we're interacting with the company, with charterers. There are many parties involved in running a ship, agents, government organisations. Some of the challenges are we have different agents coming on board. We have different parties. In a normal office situation, you would have a set group of users who need access to the technology. However, a ship that's on the move constantly has the challenge that there be different agents appointed in different ports. You will have different service people coming on board, and as the technology requires continual maintenance and upgrade, you might have different people performing those roles in different places. It doesn't lend itself to having a very consistent result. We have users, we have the crew, we have agents. In a lot of cases, we have outsourced companies performing support roles, and sometimes a lack of clear demarcation doesn't exist, where you might have an outsourcer performing the support of the office systems, the engineers supporting the onboard operational technology systems, but in some cases there might be some crossover or a lack of clarity. And we do carry risks around malware, as I've alluded to already. Malware infection can occur through email and also through browsing, and we do need to segregate those critical safety systems to ensure there is no crossover between those segregated networks. A number of companies or organisations that are interested in providing robust quality software to the maritime industry, MarITSS is one of those organisations. There are also cybersecurity requirements that have been launched from a number of different parties. BIMCO have a recommendation around cybersecurity controls that should be in place on vessels at sea. All right, so that brings us to the end of this section, and I'd like to say thank you for your attention and refer you to this book, which is an extremely in-depth read around ship automation and control systems, one of the best books that I've come across on this topic. And with that, that is the end of this section. Thank you.